if you use your right arrow and go down to 6, there's a whole mode dedicated to differential equations. Hit enter again just to be safe. In F3, you got your regular stuff. You all probably know how to differentiate, integrate, and things like that with your calculator. If you keep going down, DE solve. Maybe this is all I should show you. And then let you figure out some of the rest of it.
Okay.
Is that?
It's under.
Give us an example.
Yeah, it's under the
But you have
calculus
to put it
menu.
in there. You have to put it in differential.
X times Y prime. So the prime is, where's mine? It's yellow. Yours might be baby blue,
Okay.
but you got to go to the second
It's
button.
over the equal
So it's
button.
that one.
Yeah, it's an equal button. X, Y prime equals, say, 2Y. And just to be safe, I always put times in between. I don't think it'll yell at you if you just say 2Y, if it's a constant times a variable expression. But definitely, you don't want to put X, Y next to each other. Sometimes it doesn't recognize that you mean those to be multiplied. All right, so X, Y prime equals 2Y. And then the, what is the syntax? Comma, independent variable first?
Yes.
X, comma, Y. So you have to put in both X and Y, parentheses, and let's see what that does.
What's the add?
Oh yeah. That is their symbol for constant of integration. That's the first constant in
Oh yeah.
X squared.
What's the second constant integration symbol?
It would probably be at 2.
Oh, okay.
Yeah. So this just represents a constant.
Okay.
Constant 1 X squared. Okay. That's a way. Now, disclaimer. This on the exams, answer right after the question is asked. That's not going to be acceptable. I want to see the process, but this can give you a way to check it. Now, also be aware that you may solve it and have it in one form. You use your calculator to solve it. It may look totally different. Now, don't assume right off the bat that you're wrong, right? Because it may just be an alternate form of that same solution curve, implicit form or something like that. Okay? So that's what I always say. When it looks different, don't always assume that you're wrong. You might be right.
Like it doesn't seem to solves that one for Y that we were trying to figure out at the beginning.
Well, you can try that.
Will this do all types of differential equations?
I'm guessing probably not. Well, I don't know, because I don't know if you could put in second order. That's something to investigate. Can I do? No. And I don't want to spend all day in class.
Yeah.
Second. If I hit that, does that mean double prime? I don't know. Well, I think Y double prime equals that. I don't know. So anyway, that's a first one.
I wonder what a plus minus is.
It'll just give you constant. It won't tell you plus minus. It will say probably just constant. You have to know that constant could be a positive or a negative value depending on the initial condition. Okay. All right. So yeah, sometimes I do just forget, that I don't use a calculator a whole lot, but I want to keep you when I hear about things, share with you. Okay. I want to do what we just did with that direction field. That was all great. I want to sort of redo that and then talk about the general solution. So we have this equation. This is the same one we just looked at. Was that 100 or 1,000? 1,000. So this is one form. This is one form of the logistic model. All right. Now, an alternate form, like I said, is I could have multiply both sides of this by 1,000. That would get that 1,000 out of the denominator, 1,000 minus p. But then alternately divide the outside by 1,000. Net effect is we're just multiplying by 1. Okay, I've multiplied the inside by 1,000, that expression, and divided by this factor by 1,000, net effect multiplying by 1. So this would be our K. This is our M that we were talking about before. This is alternate form. Okay. So those constants are different. The constant here is not the same as the constant in this form of it, but we can collect those and call it a constant, and I can always write m minus p. So m represents the carrying capacity. Okay. All right, so let's look at the general logistic, the general solution. And I don't feel bad about giving it to you because we went through the whole argument for a particular problem. By the way, this is an example of an autonomous equation. I brought that up before. And, you did maybe mention, talk about that a little bit in Calc 3 in the intro to differential equations. Autonomous equation refers to the fact that the right side, this differential equation, this is the rate of change of p with respect to t, does not involve the independent variable t at all. Okay, so dp dt is a function of p only, so it's independent of time. So I'll just say its independent variable is absent. Okay, and that's what an autonomous equation is. So there is no mention of t. It's not a function of t at all. It's just a function of p and those parameters. All right, so here's the general solution. Okay. So you might recognize some of these things in here. We ended up multiplying the m and once we found k, we multiply those together up here. But this is the general solution where p naught represents the population at time 0. Okay. One thing to note with this equation, this function, what happens as t goes to infinity?
That's going to go to 0.
Yeah, this is a constant because p naught is just an initial condition usually given to us. That's the initial population. M is going to be given to us in the equation. That's one of the parameters. But this guy, as t goes to infinity, I have e to a negative power of t. The larger t is, the smaller that becomes. This shrinks to 0.
Unless
So limit as t goes to infinity of this population would be m times p naught over p naught plus this shrinks to 0 asymptotically. Okay, and m p naught over p naught is m. Okay, so this is the sort of asymptotic or carrying capacity limiting population. Okay. Also, one other thing to notice from the original equation up there, is 0 if P is equal to what? Mm-hmm.
Or 0.
Right, so if P ever hits M, that was the 1,000 in that case we did with the direction field. I get a 0 in that factor, and that zeroes everything out. Or if P equals 0. Those are our two equilibrium solutions. Okay. So any questions? Yeah.
So even though dp dt isn't a function of t, we can still say that dp dt approaches 0 as t goes to infinity?
Yeah.
Yeah,
Yeah, because the population approaches
Right.
an asymptotic, yeah.
Right.
So you can say if this is a continuous function. If it approaches m as t goes to infinity, that's a fancy way of saying that m is a horizontal asymptote.
Yeah.
So the derivative would go to 0.
But you can also substitute the function of t that you have for p into the
Yeah.
function.
And it should, yeah, it would also satisfy that. All right. Now, when we have an autonomous equation like that, this is how we can, one way we can sort of characterize these equilibrium solutions. So notice dp dt is a function of p only, as well as those parameters that we can usually find. M will often be given to us. K, if we're given enough information, we can find K using an initial condition. But anyway, dp dt is a function of p only. So here's a little graph of that. So here's t, and up here we're tracking dp dt. Where is it 0? Oh, by the way, I'm gonna put in that example that we were working on with actual numbers. dp dt equals it was whatever 8 times 10 to the negative 4th, just a constant, whatever it was. 1,000 minus p. So, oh, sorry, no, this is p. This is a function of population only. So the values of p, what we just talked about, the values of p that make the derivative 0 are 0 and 1,000. Right? If we multiplied this out, it would be 1,000 kp minus kp squared. It is quadratic in p. Upside down, quadratic. So dp dt goes through at p equals 0 and p equals 1,000. And this is what it would look like. Something like this. Right? Now, here's a question. These are the equilibrium solutions, 1,000 and 0. But what happens if P is greater than 0? What kind of values will dp dt be?
Positive.
Well, very graphic, but they're positive, right? What this means is that if dp dt is positive, that means the population is increasing over time and going towards 1,000. So what I'm going to do is impose a direction on this. And this graph shows you that over time, if dp dt is positive, it's approaching 1,000. Now, if the population is greater than 1,000, as we saw in that overhead, when the population is greater than 1,000, what do you notice?
Decline, negative.
dp dt is negative. And if dp dt is negative, then it's approaching 1,000 again.
Oh,
So you see what I'm graphing here is we're separating this. This is a critical point. Remember that? A critical point is the value that makes the derivative 0. 1,000 makes the derivative 0. If the population is greater than 1,000, dp dt is negative. And that means it's heading back towards 1,000.
It's a drain.
Mm-hmm. Well, this is it's an attractor.
It's a drain.
Oh, right.
Yeah.
Okay. Over here, when the population is less than 1,000, dp dt is positive. And if the population is less than 1,000, but the derivative is positive, then it's increasing towards 1,000. And it's going towards 1,000 and staying there, asymptotically. Now notice on the other hand, 0 was also equilibrium solution. But if the population is greater than 0 at all, what did we notice on this? Yeah, population's positive and increasing, which means dp dt is positive. So it's going, the population is going away from 0, going towards 1,000. Now here's a tricky one. What happens if p is less than 0 somehow? Now this doesn't model population anymore, but in this equation, if p is less than 0, then that's a negative. That's negative, right? And if p is less than 0 here, it's 1,000 minus a negative. That's going to be positive. So dp dt would be negative.
So it's actually
Right. And if dp dt is negative, that means the population is decreasing away from 0.
something else jumping in its niche.
Yeah. So what's happening is, if we have a small population, it grows away from 0, right? Even if the population was somehow negative, it would go away. You'd see the slope field going downward. Okay? So what that's called is, well, 0 is an unstable equilibrium. Because what that means is small deviations away from 0 eventually cause the function to diverge away from that solution. Okay? So even if I started in this model, if I started with 5 individuals, it's going to grow, and it's going to diverge away from this solution p equals 0. Yeah? Whereas on the other hand, if I start near 1,000, what happens to the population? It goes towards 1,000, so it attracts it in. Okay? It's like the Death Star with the laser beam or the tractor beam on it, just pulls those solutions toward it. Okay? Whereas this one repels. Okay? Values here near 0, it repels the solution curve away from that equilibrium. That's called an unstable equilibrium. So small deviations away from 0 eventually will cause the function to diverge. Okay? Whereas small deviations away from this equilibrium solution draws it in towards 1,000.
So is that one called the stable?
This is called a stable equilibrium.
It's French. French.
Okay. All right. So, and if we graph it like this is autonomous when I can think of dp dt as a function of the dependent variable p only. It shows what's happening. So away from 1,000, the population goes towards 1,000 again. But small differences near 0, the population goes away from 0. So this graph is pretty powerful, something like that. Okay.
So in this case, it's where p is equal to n.
Mm-hmm.
The stable.
P equals m in the logistic model is a stable equilibrium. P equals 0 is an unstable equilibrium. One way to think about it is another way is like this. If I have a bowl, okay, think about a big bowl, and I take a rubber ball and I put it at the bottom of the bowl, it's going to be at equilibrium, right? Okay. And even if I took that ball and put it up the sides a little bit and let go, what's going to happen to that ball? Yeah, it'll swirl around a little bit, but eventually it's going to settle right back down at the bottom of that bowl. That would be a stable equilibrium position, right? Now imagine one of those yoga balls, okay? It's convex or whatever, okay? And if I'm good enough, I can take an object and put it on top of that ball, right? And let it go. And it might balance there, and that might be an equilibrium. But if you're off by a centimeter, what's going to happen to that ball? It's going to roll off, so that would be an unstable equilibrium.
Or the edge of the ball.
What's that?
Example. Or the edge of the ball.
Yeah.
In the first
Oh, right, the edge of the bowl would also be
Perfectly
an
on the
unstable
edge.
equilibrium. Yeah, very unstable. Right? So it means small deviations away from that can cause kind of chaos. It will go away from that stable, or away from that equilibrium solution. Yeah.
Is it still differential equations when you bring in like independent variables that affect like your equilibriums, or I don't know?
Yeah, there's different types. We can characterize them and find them. That's kind of the. By the way, this is kind of section 2.2 stuff. Okay, so the equilibrium solutions and things like that. All right, let's do one example, and then we got some time to work on. I have an activity. So this is for specifically autonomous differential equations. Now pay attention, I'm going to switch the name of the dependent variable to y. But if I have dy dx, if this is a function of y only, that's how we characterize what an autonomous differential equation is. The equilibrium solutions are those solutions for y that satisfy the following. So, in other words, when dy dx equals 0, that would be a flat line, so it would be a constant solution. These are also called solutions to this equation, also called critical points, something that we found in Calc 1. So you guys have found critical points there. That's values in this case of y that make dy dx equal to 0. Okay. All right. So quick example. This is number 3 on page 98. So say we're given this equation, and this book loves playing with the dependent and independent variable names. So say we got dx dt equals x squared minus 4x. So x is the dependent variable here. Like the position function. So think of this as position as a function of time. So t is the independent variable. So for this equation, it's not terribly difficult. Notice it would be, well, it wouldn't be integrable, but it's separable. So first, let's find the critical points of this dt. So that's when we set the dx dt equal to 0, and we solve the values, solve for x. What will they be? 0 and 4. X times x minus 4, 0 to 4. It feels good to solve something like this again. Okay, so those are the critical points. So in other words, x of t equals 0. X of t equals 4 are our equilibrium solutions. I'm going to abbreviate equilibrium like that. Let's analyze these and find out if each of those is stable or unstable, and how are we going to find that out? We're going to analyze the sign of these critical, or sorry, dx dt. So this is like a graph what we had before, except I'm not graphing x as a function of t, I'm graphing dx dt as a function of x. Well, I know what this looks like, right? We got zeros at 0 and 4. And is it upside down or right side up parabola? Yeah, right side up. Instead of calling this y equals x squared minus 4x, it's dx dt. That's what we got there. We're graphing dx dt, it's upward. Okay, so these are my equilibrium solutions, 4 and 0. So, if x is greater than 4, dx dt is positive. What does that mean?
It's increasing, which means it's going away from 4.
Oh, right, it's going away. dx dt is positive. That means the x values are becoming larger. It's positive. So it's going away from 4. Now, on this side, if x is just less than 4, dx dt is negative, which means it's decreasing. X values are decreasing away from 4. So if they're vacating away from that value 4, this is an unstable equilibrium. Okay? Now, on the other hand, let's look at this. Let's look at x equals 0. If we have values just less than 0, dx dt is positive. Well, if x is less than 0 and dx dt is positive, that means that the x values are increasing towards 0. And here, dx dt is negative. X is greater than 0, but dx dt is negative. That means the x values are decreasing back towards 0. So that's going to be a stable equilibrium. Another way that the book does this is they create what's called a phase diagram. It's just a one-dimensional version of this graph.
It's like a side chart.
Mm-hmm. So here's my just x number line. It's literally just one-dimensional number line. I'm collapsing this down. My critical points are 0 and 4. Now, if x is a little bit less than 0, as we saw before, dx dt is positive. And if x is less than 0, but dx dt is positive, then x is increasing. And hey, the direction of this number line is increasing to the right, decreasing to the left. Okay? Whereas if x is a little bit larger than 0, we know dx dt is negative. And if x is greater than 0 and if dx dt is negative, that means x is decreasing. They're all pointing inwards towards 0. So that's our stable equilibrium. However, at 4, when x is greater than 4, dx dt is positive, and if dx dt is positive, that means x is increasing, so it's going to the right on the number line, x is increasing. And same thing on the left, dx dt is less than 0, so x values are going less than. Okay, so this is unstable. Values near 4, the x values either increase or decrease away from 4. That's unstable. Yeah.
Can we have multiple equilibriums besides 2, or do they have to be
Sure.
pairs? Or?
Sure. This happened to be a quadratic in x. Could have two equilibrium solutions.
Can they both be unstable, or does one have to be stable, the other has to?
Well, if they're unstable, then wouldn't they form another?
Right, that's a good question. If you had two unstable, they have to be going towards something in the middle. Which might be another stable. I don't know. But it's a good question.
How does this, should we see any resemblance between the local max and local min, equilibrium, or stable and unstable?
Not necessarily max or min, but it'll be a limiting value asymptotic. Yeah.
We're gonna take the second derivative. Would that tell us any information?
Concavity, yeah, it could tell inflection points. You have 2x minus 4, wherever that's 0. X values where that's 0, you have an inflection point.
Okay, but can we like use, like knowing where it's concave up or concave down?
Yeah, so, yeah, I mean, in the graphs that we did for the, shoot, start over again. Wait, do I have 2 of these? Oops. Yep. Right there? Yeah, if I went large enough on this, you'd see that there will be, there will be an inflection point somewhere. I don't have it on here. This was from 1940 to 2000. We didn't capture it. So, anyway, I do want to show you. I want to use this on